So, if there's any questions that someone wants to start with on either practice exam, if you've had any chance to look at those, we can start with those. Otherwise, I'll probably just kind of pick and choose some ones that I think we might want to work through. Yeah.
Can you explain?
Oh. All right, go ask your question. I don't know why this isn't showing up.
Can you explain like a little more about when to know when to use the population or the sample formulas, and when to use the Z tables versus the T tables?
Yeah, give me 1 second. That will be the first question if I can get this to show up. There we go. So the question was, how do we know when to use Z and when to use T tables? So probably to break this down the easiest way. So if we go so all of these are instances where you'd want to use the Z tables, right? So anytime you see proportions, whether or not it's one or two populations, anytime you see those proportions, you should automatically be using the standard normal distribution or the Z tables. Anytime you're given, this isn't showing up very good. Anytime you're given or you know the population, standard deviation or variance, right? Anytime we have the known population, standard deviation or variance, whether or not it's one or two population examples, we'll use the Z tables there as well, okay? Anytime we've got, whether or not it's one or two population examples, anytime we're looking at sample means where we only have a sample variance or a sample standard deviation, those are going to be scenarios where we're using the student T distribution. Okay? Now, if you look at the formula sheet, and I'll come back to this in a second. All right. And this is a little bit green. I'll try to get this to look a little bit better after class today. But if we go up here, if we look at kind of these confidence interval and test statistic equations, notice when we have a sample mean and we have a known variance, it's reminding us in the confidence interval equation you're using that standard normal Z table, or if you're looking at a proportion, use that Z table. If you have a sample variance where you only, if you have a sample mean where you only have the sample variance or a sample standard deviation, use the student T tables, right? Same kind of thing for our test statistics. Known population variance and proportion, we're calculating a Z statistic or a test statistic that comes from a standard normal distribution. Anytime we're looking at a sample mean with only a sample variance, so we don't know the population variance, our test statistic is a T statistic or it's a test statistic that comes from the student T distribution. Right? Same kind of thing once we go down here for the two population formulas. When we know the population variances, our confidence interval and our test statistic, we're using that standard normal, that Z table. Proportions, Z. When we only have the sample variances, student T distribution. Okay? So you can kind of reminded by the formulas in that formula sheet, but if you're trying to kind of keep track of it here, this is be another way to think about it. Is that what you were asking? Right? Okay. Any other questions you want to start out with, or you just had kind of in general? No? No questions for anyone on Zoom that you wanted to start out with? All right. So which ones do I think would be? Well, we'll review these first ones just as kind of reminding us of some old stuff. So these first few questions really go back to what kind of the information that we would have needed so that we could even understand what to do with confidence intervals and hypothesis testing. So this is the idea that I start out with some random variable, right? You know, I'm assuming that I have kind of the population mean and the population variance here. I give you the mean, give you the variance. what's the probability that someone consumes greater than 3,000 calories a day, right? So we've got the mean is 3,700, variance is 250,000, right? So what we're going to do is think about what this is. It's a normal distribution. It told us that random variable x is normally distributed. So we've got this variable x. We know it's normally distributed, and it's got a population mean of 3,700. We wanted to know what's the probability that someone eats 3,000. I think it was greater. Let me just double check that so I'm not drawing this out for a different question. Yep, greater than 3,000 calories. So we're looking for this area, right? We want to know what's the probability that somebody has 3,000 or more, right? Well, I can't really get that from any normal distribution unless I want to do some integration and plug in some values. So we're going to turn it into a z-value, or kind of convert this standard normal distribution. Once we have that value, we can then use our standard normal tables to find this area to the right, okay? So if we go to the formula sheet, oh, sorry, I hit the wrong button when I went here. So we have this normal distribution. We're looking for the area to the right. So we have to convert that value we're interested in into a z-score and then use our standard normal tables there, right? So if I'm thinking about, if I go to my formula sheet, all the way to the top here, we're just dealing with population data. We have this random variable x. We just subtract the mean, divide by the standard deviation, right? So we take that value we're interested in, subtract the population mean. Now here we want to divide by the standard deviation. I think we had the variance was 250,000. So you don't plug 250,000 in here. We would actually be plugging in the square root of 250,000. Now, if you want to calculate that ahead of time, like take the square root of 250,000, then you know that would be, your standard deviation. You could just plug that number in for the standard deviation there, or you could just plug in the square root of 250,000 into the equation. Right? So, 700 divided by square root of 250. If we do that, we should get negative 1.4. And this is kind of a reminder, if we see a value that's below the mean, remember, the mean would always have a z-score of 0, right? So anything that we see that's below the mean, we know the z-score will actually be negative. If we're looking at a cutoff value above the mean, our z-score would be positive. So we've got negative 1.4, so we'll look that up in our z-table, right? So scroll down here, negative 1.4, 0, so that first column. So 0.0808 is the area to the left of negative 1.4. Right? So the area to the left is 0.0808, which means the area to the right, would be 1 minus that. So what, 0.9192? I'm doing math in my head there, right? I think so. Okay. Any questions on that one? Okay with that? So, I think the next question, and we're working off of practice exam A here. I should have forgot to say that at the beginning. Let's make this a little bit bigger here. Now, if we think about what we're looking for when we had just drawn it out, I probably didn't even have to really work through this one, because right away, what do I know? That probability has to be greater than. Yeah, because the area to the right of the mean would be 0.5, so the area to the right of 3,000 would be bigger than 0.5. Now, if I look at that, I think there was one that was like, the answer of 0.91, but there was also one that was like 0.50 or something like that, or 0.51. What would have to be true if the area to the right of the cutoff value we're looking at is only 0.51? We would actually be looking at a cutoff value that's very close to that mean, right? Probably like 3,650 or something. So if I'm just guessing there, right away, I can cross off A. I know it has to be greater than 0.5. I can cross off D because we're looking for a probability. It has to be between 0 and 1. If I'm guessing in between these two, look, I guess if the variance was large enough, technically this could be the answer. But if I was just going to guess and didn't want to work through this problem, I'd probably be going for B was the more likely answer, right? So on this one, you could narrow down to 2 answers pretty quickly. And then from there, even an educated guess probably could have got this one right, okay? So what's the probability that a US consumer consumes more than 4,200 or less than 3,200 calories, okay? So 3,200, less than 3,200, or greater than 4,200. So what's kind of the area that we're looking at here? So we've got the same distribution, but now we want to know, centered around that 3,700, what's the probability that we see less than 3,200 or greater than 4,200? So let's do this one first, kind of find that area. We'll turn this into a test statistic, right? Same thing as the last one. It's just a matter of plugging our values into that equation to find a z-score, okay? So plug in 3,200, 3,700 was our mean, square root of 250,000. Right? If we do that, we'll get what? So 500 below should get a z-score of -1, which this is sometimes where figuring out what the standard deviation is might help. You don't have to do this step, but if you were to take the square root of 2,500, you'll see that our standard deviation was 500. Okay? Or sorry, the square root of 250,000, not 2,500. So we get a standard deviation of 500. Well, notice we were 500 below the mean. The interpretation of our z-scores are the number of standard deviations away from the mean. So here we're just 1 standard deviation below the mean. Okay? So we want to find this area. We go to the table, look up -1. Well, this is nice because we want the area to the left. That's what the table gives us. So -1.00, 0.1587. Okay. So we've got this area is 0.1587. Now, I can do the same process, turn this one into a test statistic. Then I'm looking up that z-score. It'll give me the area to the left. I can subtract it from 1 to find the area to the right. But I'm probably giving you these numbers to make it a little bit easier. What should the z-score of 4,200 be? How far away is it from the mean? 500. This one was 500 away as well. So if this was a z-score of -1, I don't even have to use the formula. I know that this one will have a z-score of +1, right? Because it's the same distance away from the mean, so it's going to have the same z-score. It'll be the same number of standard deviations away. It's just now it'll be positive, right? And I could look that up in the table, find the area to the left of 1, subtract it from 1 to get the area to the right. Or I could just say, this is a symmetric distribution around this mean of 0. So the area to the left of -1 will be the same as the area to the right of +1. Right? So now I've got those two areas. Now I simply just add them up, right? 0.1587 plus 0.1587, or kind of multiply it by 2 since they're the same value. So we get what? 0.3174 there. Okay. Now, if I do ones like this, typically I'm pretty nice and I'll give you kind of things that would be the same distance away from the mean. Or something else I might do is say, what's the probability it's less than 3,200 or greater than 3,700? In which case you would find this and add what to it? 0.5, right? Because the area to the right of the mean is 0.5. Right? So anytime I'm kind of giving you one where you kind of have two areas, the other one, there's probably a way where you don't have to actually go through and calculate the test statistic. There's probably some other knowledge about it being symmetric or about the area to the left or right of the mean that you could probably use. Now you can go through the whole process, especially if you're just trying to kind of double check your answers, but if we kind of just remember the principles and kind of make that one a little bit easier, okay? So let's say I take a sample of 25 people, okay? What will the mean and the standard deviation be for the distribution of my sample means? Okay. So once we take a sample, we know the mean of our sample means should just be like there's no formula for that, but we know the mean of our sample means is always going to be just whatever the original population mean is, whatever we sampled from. We also know that the variance of our sample means will be the original variance divided by our sample size, okay? So if we're thinking about what we have here, we're sampling from this distribution, our sample means should be distributed normally, since this original variable was normally distributed. We didn't even need the central limit theorem there because the original data was normally distributed. We'll get a mean of 3,700, so either B or C here. And then the standard deviation, well, if the variance is the original, if the variance of our sample means is the original variance over our sample size, then the only other thing we would have to do to get the standard deviation is take the square root, right? So here, if we were thinking about the distribution of our sample means, it should be normally distributed around whatever that original population mean was, and our standard deviation would be the square root of the variance of our sample means, which is the original variance of the data over our sample size. So what, the square root of 250,000 over 25? So I'm thinking, I think this is 100. I'm looking at this in my head, right? Okay. I'll get out of the way there for the video too. So we've got our standard deviation and our mean there. Give me 1 second, Ross. So 3,700 and 100, right? And I think I just saw something. Hold on. Hopefully this wasn't too long ago. Yeah, after, let me finish this out and then we'll kind of jump to those. So what's the probability that on average the calorie consumption of this sample of 25 is less than 3,550? Okay. So now we're looking at the distribution of our sample mean. So if we want to turn that sample mean value of 3,550 into a z-score, we're going to use this equation. Okay. But remember, kind of that equation, what it's really saying is, so I'll kind of write it up here and then add something to it. Remember, this denominator just represents the standard deviation of my sample means. So if I'm pretty confident here that this was the standard deviation of my sample means, this denominator is actually just 100, right? Because if I plug 250,000 and 25 into here, I'm getting the same thing that I found before, right? So what I could do is say, okay, look, I want the probability that I see something, I think it was less than 3,550, plug that value in to my sample mean. I've got my population mean of 3,700. My denominator is 100 here. So if I'm looking at this, I should get a z-score I think it's negative 1.5. Right. I would then look that up in my standard normal table, and that would be kind of the area that I wanted or the probability that I saw something that was 1.5 standard deviations below the mean or anything even further. Right. So if I go to that standard normal table, negative 1.5, 0.0668, right? So 0.0668, right? That one's pretty straightforward. So this one's going to be very similar. It's just we have a different cutoff value, I'm not going to walk through this one completely because there probably are other ones that are more useful for us to spend time on. But all I would do, it's the same setup, but instead of 3,550, I'd use 3,500. Then whatever the area to the left is of 3,500, right, whatever that test statistic ends up being, I would, so greater than 3,500 and less than 3,700, right? So this is one, I won't work out all the exact details or all the exact values because you have the answer key kind of has all the formulas kind of set up for you. But real quick, just to kind of give you some insight on how to do that one. We're dealing with the same example, but we wanted the probability of being in between 3,500 and 3,700. Right. So what I'm going to do here is turn these into z-scores. Well, right away, what's the z-score here? The z-score is not 0.5. Z-score is 0. The area to the left is 0.5. Right? I then would turn this into a z-score, look that area up, and that might be, I don't know, something like 0.02. I don't know exactly what it ends up being. But how would I find the probability that I was in between those two values? I would take that area to the left of 0, subtract the area to the left of whatever this test statistic ends up being, and that would give me the probability of being in between the two. Okay. And so I could kind of flip-flop these as well. Like when we're looking at the distribution of sample means here, I asked you a question where you had to find the probability of being in between two values. Maybe I do that when you were just looking at the original variable x, right? And then maybe for the sample means, I ask you a question where, well, what's the probability I'm less than this value and greater than this other value, right? I could like kind of flip-flop those. But really, it's the same procedure, right? Once I get to my z-scores, it all looks the same. Right? All right, so Ross, was it 22 and 23? Yeah, so let's go down here. Probably some newer stuff here. Okay, so let's say we've got kind of two sample proportions, and we've got our two sample sizes from both those groups. So 37% of men own guns, 31% of women. We're looking for the true difference between kind of male and then female kind of gun ownership here, right? And how did I set this up? I said men were group 1, right? So P1, group 1 is men, right? So when we're thinking about is the difference between male and female gun ownership, is it different than 0? So we assume the opposite is true. We assume it is equal to 0. What would our test statistic be? Well, actually, if we're calculating the test statistic, that doesn't matter, right? Because it doesn't matter what type of tail test we have, doesn't matter we're going to calculate the test statistic the exact same way every single time. So if we go down here, this is where we have this P bar that we first need to calculate, right? So I'll first calculate P bar, then I can plug that in here, and then I can calculate my test statistic, okay? So I'll write that out here in just a second. But one thing I do want to point out is if I think about what I have here, right? So male is 0.37, female is 0.31. So even if I kind of don't worry about this for a second, remember, what's in my denominator for every test statistic that we calculate? The denominator always represents some type of standard deviation, right? So when I'm thinking about that test statistic equation, and I've got this guy here, and we could put an assumed true difference here, but I already told you that we're always going to use 0, so that's why that's not there. I then have what? P bar times 1 minus P bar, 1 over, right? What's in this denominator represents the standard deviation for the difference in those sample proportions. So if it's a standard deviation, I know my denominator is always going to be positive. So this is 0. I can essentially ignore that. Whatever difference I find for these two population examples is going to tell me the sign of my test statistic, right? Because when I assume that the true difference is 0, then when I'm thinking about the distribution of that sample difference, I'm assuming that it's around 0. So whatever sample difference I see is going to tell me whether or not I'm above or below kind of that assumed true mean, or what the sign of my test statistic is. So here, if I plug in 0.37 and 0.31, my difference is 0.06. So I know my test statistic has to be positive. So right away, if I look at, not this, if I look at these possible answers, right away I should be ruling out A, right? Now I could probably rule out B as well because it just seems like a really low test statistic. If my answer was B, what my test statistic tells me, remember, it's either a Z or a T value. Here it would be a Z statistic because we're dealing with the proportions. Oops, sorry, we're dealing with proportions. I would have had to find a difference that was really, really close to 0, right? Right? If I wanted that test statistic to be 0.029, I would have had to found sample evidence that was really close to 0. Now, 0.06 might seem like it's close to 0, but remember, when we're dealing with proportion examples, what's the greatest difference I could find? So what's the highest my first sample proportion could be? It's proportion. So the highest value is, what value does a proportion have to be between? Lowest it can be is, so the difference that we could see could be -1, right? But a proportion is telling us a probability. The lowest probability of something occurring is 0, right? So let's just assume for a second that this was 0. The highest that proportion could be would mean everyone, right? So 100% or a proportion of 1. So yeah, we could see a difference of -1, or we could see the highest difference we could ever see is +1. So seeing a difference of 0.06 isn't that really that close to 0, right? I mean, these are the highest values we could see. In practice, we're never going to probably see that, right? You have to think about if all men owned guns and all women didn't, or vice versa, right? It's just not a very likely outcome. So, we actually go to calculate this test statistic, it's probably going to be C or D, right? I could rule out A though, because I know it's not negative. So, the answer key kind of has this where I plug all those values into those formulas. I think if you're kind of working through this, let me open up one of those right now. If you're working through these problems, I can write it out if you really want me to, but all I'm doing is once I identify that equation I need to use, I calculated P bar, right, ends up being 0.34 after I plug in my sample sizes and my sample proportions. I then go to that Z statistic equation, plug in P bar here, plug in my sample sizes, my sample proportions, and I get that test statistic as 2.002. Right? And then 23, well, let's not look at the answers first. 23 says assume that test statistic you found was 1.45. So here's another thing I want to point out, and I think I mentioned this on the first exam. If I give you an assumed true value, don't read into it at all, right? Don't say, oh, well, this was 1.45. I got a test statistic of 2.002 on the last problem, but maybe it's like actually 1.645 because that's closer to the assumed true value he gave. I'm giving you these assumed true values for completely unrelated reasons to whatever the actual true value is, right? In fact, I might do something, sometimes it's going to be wildly different because the test statistic wasn't very interesting, so I wanted to make it a more interesting problem or difficult problem or vice versa. So don't read into these assumed true values at all, okay? So assume that you found this test statistic of 1.45. What would the p-value and the outcome of the hypothesis test be? So here, I guess I forgot about the second half of the problem, and really you're only identifying the p-value. But we can think about what the rejection decisions would be, okay? So if my alpha is 0.05 here, and I've got what type of tailed test? Two-tailed test, because I've got a not equal to sign in my not equal to sign in my alternative hypothesis. What I'm really thinking about is this, okay? I had some original data. You're being nice to Jack now? Yeah. Okay, so I have some original data, right? That I know the difference of sample portions is is between 0. We found, I think, like what, 0.06. Once I turn that into a test statistic, I was told, assume that test statistic was 1.45. If I want to find the p-value, remember the p-value is the probability that I saw sample evidence as far away from that assumed true value or assumed true difference as I did, or anything further that would go against that null hypothesis. So I'm kind of thinking about this area. But for a two-tailed test, it would have been equally as likely for me to see something that was, say, 1.45 standard deviations away from the assumed true value, or even further, but on the other side, right? Instead of being above, being below, right? So for a two-tailed test, I can find the area of this tail. I know they have the exact same kind of tail on the other side, so I would then, multiply it by 2 to get my total p-value. So I've got 1.45, right? I have a proportion example, so I can use that standard normal distribution. So I can go to the table, look up 1.45. It'll tell me the area to the left, right? I'll have to subtract it from 1 to get the area to the right. So I go 1.45. Z table. So scroll down here. 1.45. So 0.9265. Okay. Now, one thing here, let's say that you took that 0.9265 and you thought that that was the area in this tail, so you multiplied it by 2, you get what, 1.8 something? Right away, you know that answer can't be right, because a p-value is the probability you saw something as far away from the assumed true value or further, right? Probabilities can't be greater than 1. So if that happens, you probably know that, oh, I should have subtracted something from 1 at some point, right? So I go back down here and I remember, oh yeah, the area to the right, or sorry, the area to the left here was 0.9265. I wanted the area to the right, so I had to subtract that from 1, which leaves me with what, 0.0735. I then have to multiply that by 2 to get my total p-value. So my p-value there is 0.1470. Okay. Now, what's another way I actually could have done this one instead of like forgetting, like to avoid kind of subtracting from 1? Well, remember, for a two-tailed test, it was that I could have seen evidence on the other side of the distribution that went against the null. It would have been equally as likely. So I'm really thinking about something that was 1.45 standard deviations below. Then I could just look up that z value of negative 1.45. The table would give me the area to the left right away, which would be that 0.0735, multiply that by 2, and I get the same answer. Any questions on anything there? So what this is telling me is the probability that I saw the sample evidence that I did, if in fact this was the true value, there was about a 14.7% chance that I saw a sample difference that was that high or even higher. So I think about my rejection decision here. I only reject if the p-value is less than alpha, right? We compare to our kind of typical alpha values. Is my p-value less than 0.1? No. Okay. 0.14 is not less than 0.1, so I failed to reject. Well, if it's not less than 0.1, it's not going to be less than the other two. So this is an example where I would fail to reject at all 3 of those significance levels. Okay. Any questions on that? Now notice here with a two-tailed test, it was important we didn't forget this step where we multiplied it by 2. Because if I didn't multiply it by 2, what would my p-value have been? In which case, I would have actually thought I could reject it at the 90% level or the 10% significance level. But I couldn't because the actual p-value was higher. Okay? Any questions on that one? Or if something changed? Or... Is that going to answer those questions for you, Ross? Let's see if I answer that. Okay. let's,
Actually, I have a question.
yeah.
So if this was a left tail or right tail test, you just wouldn't multiply it by 2 and then just find that p-value and then reject it?
Yeah, let's say I found the same setup, but I had a right tail test.
Right.
Now, if I see sample evidence on the other side, it actually supports the null. Because the null for a right tail test, the null would be that it's less than or equal to. So if I see evidence that would be less, well, that supports the null. My p-value is kind of, you know, I sometimes probably am lazy and I say it's the probability we see something as far away from the assumed true value that we did or even further. But kind of the additional statement you need in the end there is that that goes against the null hypothesis, right? And that's why for a two-tailed test, evidence on the other side would also go against the null and be equally as far away from that assumed true value. For a right-tailed test, evidence on the other side actually supports the null. So we won't be rejecting it all there. So we would do the same process, find the test statistic, same way, find that area to the right, and we're done. So for a right-tailed test here, we could have rejected at the 10% level. And that might kind of seem weird, but if you think about it, for a right-tailed test, it should be more likely we can reject the null because there's only values on one side of the distribution that actually go against it. So like, you think about alpha is no longer getting split up into two sides. So our threshold is kind of like moving backwards, right? Like our threshold for what we're willing to kind of accept as the number of standard deviations away, like our critical values are going to be getting closer to 0 because it's alpha is no longer being split up into two sides of that distribution. Any other questions on that one or anything? What if this changed, or what if, like, those are actually good questions to ask. Like, well, what if this changed? What would we do, right? Because I can only work through, I mean, I guess we could probably figure out how many combinations of left, right, two-tailed tests with the different examples we have. You know, I probably won't go through every single one. We've probably gone through most of them, but we could always kind of do a two-tailed, two population, unknown population standard deviation, right? But I could do a right tail, or there's a lot of different combinations, but the principles are all the same, right? So we can apply these principles to all of them. All right, let's see what's in the chain. Okay. All right, where are we at on time? All right. Let's see if there's one I want to go through here that I know that I wrote. I want to do a t-value one. Is this a student t? Okay. I have one down here. Okay, let's start working through this one. Problem 18. So I've got kind of Ohio, Indiana. Typing this up for the practice exam. I guess it wasn't complete, but like we're looking at BMIs here, right? So we want to know if Indiana is healthier than Ohio. I get some sample BMI data, and I calculate my sample variances, right? So sample sizes for the two groups, sample means, sample variances. We don't have a known population variance, so right away we should know I need to use the student t distribution. So if I think about kind of building this 99% confidence interval for what the true population mean is, and here I'm told assume the degrees of freedom is 50. So this would have been the one where, and I think I have the formula on the formula sheet, although I'm not going to expect you to use it. We kind of have this nasty formula that we'd have to calculate the degrees of freedom for. I'm telling you, I'm not going to make you do that in the exam. I'll give you these assumed true values of like 50. Right? So I'm going to build a confidence interval using that degrees of freedom of 50, and I forget what the level was, but whatever alpha is. So this is my equation, right? I plug in those two sample means, I plug in those two sample variances, plug in those two sample sizes. When I'm doing a confidence interval, really the only difficult part after I've identified the formula I need to use is finding like the z or the t value. So here I'm going to find the t value, but I'm going to have to remind myself what confidence level we wanted, which was 99%. So my alpha would be what? The 99% confidence level. Alpha is just the area outside my confidence interval in decimal form, so 0.01. right? 1% would be outside the interval in decimal form, 0.01. I go to my student t-table. 0.01 is alpha, but remember, I have to divide that by 2 because I have 2 sides of my confidence interval. So alpha over 2, 0.01 divided by 2 would be 0.005. My degrees of freedom, I said assume was 50, so I keep scrolling down. 2.678, all right? So now that I have that value of 2.678, I can plug that in, and now it's just a matter of getting that entered into my calculator correctly, right? 2.678, plugged in the other values already. Now, if I look at kind of what I was given, group 1 is 27, group 2 is 29, right? We're kind of told here, group 1 minus group 2. So I'm building my confidence interval around the sample difference of -2, right? So what I'm thinking about doing here with my confidence interval is I'm building it around that sample difference I found, which was -2, okay? So -2 should be smack dab in the middle of my confidence interval. If I just look at these possible answers, I can rule out D right away, right? -2 is not even in that confidence interval. If I look at these a little bit closer as well, I can actually rule out C too. Because look at -2 would be a lot closer to -1.2 than it would be to -4.2, right? So technically I could actually rule out C here as well. The other two, I think it's actually in the middle of them. So, we could limit it down to 2 answers, but then we'd actually have to kind of do the work here. So once we plug those values in, I don't know, we've got the, like I said, we've got the answer key here. So me kind of writing out the equations, we're plugging things in, probably not the most useful or the best use of our time. So once we plug all those numbers in, we get what, -5.1 to -1.1. Okay. Any questions on that one? Okay. So what if I'm looking at this test statistic, right? So our test statistic, same kind of idea as what we had talked about with the difference in the proportions. Once we go and look at that formula sheet, here's our test statistic equation when we only have sample variances. That denominator still represents a standard deviation. So this difference that I find, the sample difference I find, tells me the sign of my test statistic. We found that the sample difference here was -2. So I can rule out A right away, right? I know that my test statistic has to be negative. From there, it's just, it's really just a matter of getting those values plugged in and being confident with kind of using my calculator or using Excel, if that's how you want to kind of, use Excel as a calculator, to getting that test statistic, okay? So if we do that, all right, we're just plugging those values into that equation, we get about -1.7. Like I said, I'm kind of going through this quick because me writing the numbers in I don't think is that useful. So we've got -1.72. I'm guessing on the next one though, I give you an assumed true test statistic again, right? So I give you this assumed true test statistic. So if you got 19 wrong, you won't automatically get 20 wrong, right? If I'm trying to find p-values or make rejection decisions, if I got the test statistic wrong, all bets are off if I get that next part right. So what type of tailed test do we have here? Left tail, I look at my alternative hypothesis. There's a less than sign. So left tail test, which really means that I'm thinking about, when I'm drawing this out, I'm dealing with the left side of that student t distribution. The blue one shows up a little bit better. So I found a sample difference of -2, and I'm assuming the true difference is 0, right? Less than 0, or I assumed it was greater than or equal to 0. So I'm dealing with this left side of the distribution. I want to turn this into a test statistic that is a t statistic. It's coming from the student t distribution. The probability that I saw that test statistic or anything further from the assumed true mean, right, is going to be in that area, and that represents my p-value, right? So I've got a left tail test. I think, was it negative 1.55? I think I told you to assume the test statistic was equal to. Let's see. It's probably, yeah, negative 1.55. So if I think about what levels would I reject at, I thought this was a p-value. This is critical values. I'll show you both, sorry. If I wanted to find the p-value, this would actually probably be one I wouldn't ask you on the exam, because at degrees of freedom of 50, I can't find that negative 1.55 here. Now, remember, if I have a left-tailed test, I can still use this student t-distribution. I just have to remember, I can kind of think about all these values as negative for a left-tailed test, right? Because it's a symmetric distribution. Now, I might do something like give you a test statistic of, say, negative 2.403. Or actually, no, negative 2.009, right? So if I gave you a test statistic of negative 2.009, you know the p-value would be 0.025, right? But I'm not going to make you kind of like put bounds on that p-value, right? If I give you an assumed true test statistic for the student t table example, I'll give you one of these exact values. But the question wasn't asking for the p-value. I assumed that's what I was going to ask, but I actually asked you for the critical value, right? So I asked you for the critical value at the 95% confidence level. So what we're thinking about there is, what critical value gives me 0.05 in this lower left tail, right? And then once I find that critical value, my rejection region is anything that would be kind of further away from that assumed true value of 0, right? Or kind of draw the arrow into the tail. So if I have degrees of freedom of 50, and I want 0.05 in that lower left tail, 1.676, but remember, the student t table will give me the value, but I have a left-tailed test, so it's going to be that value, but negative, right? So I can get the value that I want, like the absolute value for a left-tailed test from that student t table, but I have to remember, it's a left-tailed test, my critical value should always be negative. I then had that test statistic, of assumed true test statistic of negative 1.55. So if I plot that, it's not quite in my rejection region. Just slightly outside of it. So the final answer there would be negative 1.676, and I fail to reject, or I do not reject the null hypothesis. Yeah. Why would I have it as C? Oh, I probably thought it was, I probably put it in there as a two-tailed test, but it's not. Let me see. Yep, that is not right. I'll change that and re-upload this, right? It should be answer A here. Right? Answer C, I'm guessing, would be if I had a two-tailed test. Yeah. Okay.
So,
yeah.
So you don't have to divide the 0.05 by 2?
Not if I have a left or a right-tailed test. I only divide it by 2 if I have a two-tailed test. Right? That's what I was saying earlier, where alpha is the total area in your, this is how I'll write it, maybe it makes a little bit of sense. Alpha is the total area in your tails. If you only have a tail, it's the area just in that tail. If I do have multiple tails, then it's the area in those tails. Okay. All right, we're running out of time here, but we'll kind of pick up. We'll keep going through more examples on Friday. The exam's going to have, I want to make sure I don't go over too much time here. Okay, so the exam's going to have 20 multiple choice questions and then kind of 2 short answers. The total points of the short answer is like 25 points, and the total points from the multiple choice will be 75. Like 75% is multiple choice, 25% is a couple short answer questions, okay? I probably give you, I think I mentioned last class, an hour and a half, so 90 minutes. Should be more than enough time, I think, for the length of it. We'll talk more on Friday. I'll have the exam open on Friday, even before class, but we'll kind of do some more review Friday. If you want to hold off on taking it, and then you'll kind of have the entire day of Friday and the weekend to take that exam. Okay? All right. See you guys on Friday.